And you guys missed all of my wonderful impromptu chit-chat that was, like, completely inconsequential. I was just commenting on how the sun's out today, and that's kind of nice. I was also asking after your state of affairs, if you guys are doing all right today. Good lord. See, it's this button right here. That's the problem. I just need to get onto it. Yeah. Anywho. So. My goodness, why do I have this open 3 times? Very strange. Anyway. Boop. How is Marimba doing? Good question. I don't know. Maybe she could mysteriously make it onto the stream tonight if some agent of justice were to deliver her. Yay! Here she is. She's settling in quite well. Say hello to all of the students, little Marimba. Are you just the most famous of internet kittens? Nope, you don't. Oh. Squirmy. Anyway, there she is. She's happy. Actually, it's kind of funny. We were kind of worried that our existing cat would not necessarily like her very much, but it turns out that they actually get along quite famously. Martin is our other cat, and he was, like, they were snuggling on the bed and giving each other, you know, grooming kisses and stuff, and it was very, very, very cute, and my wife got some photos. It was fantastic. Anyway, we should talk about stuff. Yes. So, the previous slide set is, like, super, super critical for you to get. Like, I know that the stuff inside of it is a little, if you've done any programming at all in the past, then that stuff should be reviewed, right? The for loop, while loop, if statement type stuff. Not necessarily for loops, but, you know, that stuff is extremely essential. Extremely essential. The other stuff that it's also, post them on Piazza. Post what on Piazza? Yes. So this slide set is going to be completely essential to your success in this course, in the same way that the last slide set was completely essential to your success in this course. If you don't get this stuff, you might run into a lot of issues down the line when you try to do literally anything else, as pretty much everything in the course, excuse me, you can kind of think of it as, like, in tiers. The sort of the material that's supporting everything in this course is the stuff in slide decks 2, 3, and 4. Everything else builds off of that and supports that. It's like second tier information. Yeah. Oh, yeah. Yeah. Okay. All right. Maybe at some point. Right now we're lecturing. So, what we're going to talk about today is we are going to talk about ways that you can organize the data that you're using. It is often the case when you're programming that you require sequential access to data, or access to data that's slightly different from the variable name assignment sort of structure that we've been going with so far. The essential concept is that you can group many variables together into a structure of variables, and that is what we're going to be talking about today. So, let's get to it. Today we're going to be talking about lists, sets, dictionaries, problem solving, and I had my thumb out for some reason, which is unusual when you're counting. But anyway, the thumb is what we already talked about, which is the introduction. So, let's talk about lists. So, we talked about tuples last time. Lists are very, very similar to tuples. They are interchangeable with tuples a lot of the time. The main difference between lists and tuples is the fact that lists are mutable and tuples are not mutable. Mutability is a very important topic. So, tuples and lists are both what are called ordered collections. All of these data structures that we're going to be talking about could be called collections. Elements don't have to be of the same type. Elements can occur multiple times. So that's, of course they can. Why wouldn't they be? Again, the difference is mutability. Also the way that you declare them. So if you're declaring a tuple, you're using round braces. If you're declaring a list, you're using square braces. Or there, square braces. I don't know, then maybe that's more square. Maybe these are curly braces, I'm not sure. Anyway, so if you want to declare a list, it's very, very simple. Hold up your handy-dandy Python interpreter, find some place to put stuff, and create a list with square braces. 1, 2, 3, 9, whatever, Mom. There we go. That's a list. If you want to display what the length of the list is, get the size of it, you use len. This should be familiar to you by now. This is the same way that you get it off of a string and off of a tuple. And, in fact, as we discuss sets and dictionaries, we're going to see that length is the function that's also used for all of these functions, all of these data structures as well, to get the size of them. This is actually a desirable property in programming. This is sort of a side point. It's called polymorphism. It took a moment to recall the term to my mind. So when you have a function that contextually does different things, or it does the same thing when different things are applied to it, the idea is that it can handle multiple different types of inputs, right? So length can take a string, it can take a tuple, it can take a list. These are reasonably easy things to cast for one another, like you can convert between these relatively easily. But something like a set or a dictionary, these are somewhat exceptional cases. There's no straightforward conversion from lists to dictionaries and back again, or to sets for that matter. So the fact that length takes inputs of all of these different types and still has roughly the same meaning, this is known as polymorphism. Poly meaning many, morphism meaning shaped. If you are a fan of the Dungeons and the Dragons, you will recognize what a polymorph spell does. Or a true polymorph, as it is known to people with 7th level spell slots available, I believe. Anyway, polymorphism. It's a thing that if you go on to do other courses, you may hear that word again. So, like, part of the purpose of this course is to familiarize you guys with some of the language that's used by people in computing, right? So that you can speak computer to people. But anyway, with respect to the manner in which you get stuff out, in this particular case, it would be an int saving throw, yes. You get stuff out of a list in the same way that you get stuff out of a tuple. You grab it by its index. So in this particular case, the index at 1 is 2. The index at 4 is whatever, mom. Anyway, the manner in which you change the... Well, I just about got ahead of the slides. So that's how you access the elements inside of a list. Same way as you do for a tuple. Conveniently enough, Python allows you to do that for strings as well. So we have a difference here, though. There's a difference between... This is where we start getting into the differences between tuples and lists. So if, for example, I declare a tuple with round braces containing very similar elements, or something like that, if we want to modify the values that are inside of a list, we can use an assignment statement in order to do that. So if we then ask it to tell us what that is, you can see that the value at position 3 has been replaced with an equally sarcastic quip. However, if we attempt to do this with a tuple, you will see that we get a type error. Oh my goodness. I see the D&D crowd has descended. Actually, I never actually played D&D as a character. I had a friend group that I was DMing for, and I wasn't very good at it, and they weren't very good at it either, and we all just it slowly deflated like a flan in a cupboard. But anywho, the trick with tuples is that you can't actually assign to them. This is because a tuple is an immutable object. Immutable. As opposed to a list. Lists are #mutable. And this is part of what that means. This is part of what it means for a list to be mutable. So you might say to yourself, this is a question I commonly get, so if tuples are immutable and lists are mutable, and the fact that a list is mutable allows us to do useful things with a list that we can't do with a tuple, tuples being more restrictive, why on earth would we ever use a tuple? Why wouldn't we always use a list? And in fact, why do tuples even exist? The answer to this question is that there's a price to be paid for mutability. Inside of your computer memory, when you allocate memory to a larger data structure, say you're putting this tuple into the memory of the computer, right? You know how much space that tuple is going to take up, right? You can calculate how many bits you need. You can just plunk it there in memory and say, okay, I don't have to worry about any memory management jiggery-pokery. This thing is always going to be this size because it has to always be this size, and that's it. Oh, yes, sorry, it's octothorpe mutable. So trains of thought. It's going to be super easy to derail me today, and don't try, chat. So the problem with a list is because it's mutable, the size of the thing can change at any time. Now, the problem with memory is that when you set aside a certain amount of computer memory for a particular amount of data. You can imagine like setting up a bunch of cardboard boxes in front of you and saying, okay, I'm going to put a number in here, I'm going to put a number in here, I'm going to put a number in there. The memory is shared through by all of the things that are running on your computer. So there are constantly a large number of computer processes, computer programs that are making demands on a system's memory all simultaneously. Or hopefully not completely simultaneously, hopefully at different intervals, slightly spaced out. But anyway, once you have declared a certain amount of memory and said, okay, this belongs to this Python script that this guy wrote and is trying to execute. I know it's going to be an infinite loop, but I'm going to let him try anyway. The other processes on the computer will begin making claims on memory that's adjacent to it. So it might say, okay, you've got that much. The next amount of memory I'm going to give to the thing, I'm going to give that to the podcast that you're listening to while doing your homework, etc., etc. So when the problem is, if the size of the data can change, where do you put that data, right? It would be taking pieces of this mutable data structure and putting it in what's called disjoint pieces of memory. So if you guys have ever run a disk defragment operation, and I highly recommend this. This is kind of like routine computer maintenance that a lot of people just don't understand needs to happen every once in a while, but plenty of people have computers anyways. Like, people will have a laptop for like 3 years, they'll think that the laptop is getting getting old, and that's why it's so slow. But what is actually happening is that the disk is getting fragmented and everything's just taking a long time, because to read a file, you have to read memory from 3,000 different locations on the hard disk. And what a disk defragment operation does is it takes all of the fragments of any file and it allocates them to continuous memory, in technical terms. Unless you have an SSD, then disk defrag does nothing. Possibly. Hey, give me a break, man. I'm used to magnetic media. Is that really true? On solid state drives, disk defrag doesn't do anything. Because you would think that on a solid state drive you would still have a fragmentation problem. Maybe it's just that the access time is so fast that it doesn't matter that the data is strewn all across the disk. Anyway, interesting technical problem. But anywho, this is a very similar idea to the idea of, the point that I'm trying to drive at here is when the data structures that you're working with are mutable, that means that they can have more memory allocated to them dynamically. This means that essentially you're doing the same thing to your memory that you're doing to your hard disk when it becomes fragmented. It just takes more time to get through it. Now, of course, your random access memory it doesn't have a permanence problem in the same way that a hard disk does, right? In a hard disk, if your files are fragmented, they stay fragmented until they have been defragmented, right? That's why it's important to defragment your hard drives every once in a while, as long as they actually are a hard drive, apparently, according to Nick W. But with respect to the memory gets wiped. Whenever you close the program, all of the memory that was allocated to that program gets reallocated to the system, can be used however it wants. It's a lot less permanent, so it's a lot less much of a problem. However, it just makes it slower. The point that I'm trying to make is that mutable structures, while very convenient, make things less fast. And I won't belabor the point any further. So, here once again, we have one of our handy little tables for quick reference for various operations that you can apply to strings. You may notice that there is a significant degree of overlap between these operations and the operations that we were talking about with respect to strings and tuples. So, if you wish to declare a list, you use square braces. If you wish to declare an empty list, you have to declare it with square, like just nothing in the square braces. This is one of the few instances where that actually works in Python. Normally, since the characters are shared among a great number of different things, you have to use slightly different characters, but not in the case of a list. I think that the thing for an empty tuple is like that. Let me see. Nope. Well, you can always declare it as an empty list and then convert it to a tuple. That works too. Maybe it is just like that. Oop. Let me see. I'm trying to get the syntax. Yep, that works too. Okay, never mind. Okay. Ooh, we have a technical explanation. It's due to how they read. Okay, so this is about defragmentation on solid state drives. It's due to how they read the data. The magnetic drive has movable. Okay, so very good to know. In summary, the difference between a solid state drive and a hard drive, for those of you who may not be familiar with the down hardware stuff, you have a magnetic disk and you have a read head, right? That read head has to physically move to the location where the memory is stored, and then it reads the bits that have been encoded magnetically on that disk at that specific location. Because it's a physical object, it has to physically move, and that takes time, especially when you're reading a lot of data. With a solid-state drive, everything is done electronically. A solid-state drive is essentially a very, very large, complicated, multiple-layer computer chip that just stores permanent memory. It's actually not completely dissimilar to something like, umpteen gazillion flashcards or what are they called? SD cards smushed together. And because there's no moving parts, it's a lot faster. That's why SSDs are faster. However, the one sort of problem with solid-state drive technology is that there is a limited number of write operations that you can perform on it that before the chip starts to degrade. And it's a large number. You don't have to worry about a solid-state drive failing, probably within 20 years of use or something like that, like normal use, right? However, there are certain types of operations that are really bad for things that have a limited number of write cycles before failure. One of them is just taking all of the memory and moving it everywhere and not actually doing anything with the memory except to just move it all over the place. So yeah, I can see how defragmenting a solid state drive would be problematic if you did it too often. That said, if it's magnetic, defrag that man. That you can put that on a t-shirt. Yes. Anyway, that's more stuff from like computer engineering than computer science. Most computer scientists don't care about that kind of stuff. That's more of an engineering point. Computer scientists are more interested in the abstract realm of hypermath. Anyway. So anyway, we've already discussed indexing. You can do list slicing in the same manner as we were doing with strings. And I think we've got a few slides on slicing in this slide set, so that'll be good. list concatenation occurs with the plus operator. So if we've got list 1 is this, list 2 is that, then we can concatenate these lists using plus. Concatenate means smush together. So that's good. That's another example of polymorphism, by the way. This plus operator does very different things depending on its context. Again, we can take the length of it. Here's an interesting one. Test for set membership. So you can get a Boolean. This returns a Boolean as its result. But if you want to see if some value is in some list, you can just use the in keyword. This is a different use of in than the in that's used in for loops, by the way. It does a very different thing. In this case, this is a test for collection membership. That's a more precise mathematical way of thinking about it. And of course, you can do the Boolean negation as well. If you wish to repeat the list, then you use the multiplication operator. There you go. If you wish to count the number of occurrences of some element in the list, you use count. And to get the first index, you use index. These are all things that we discussed, when we discussed tuples. So, we have, however, because lists are mutable, they have additional things that you can do to them, unlike tuples and strings. So we have some additional functions. These are technically methods. They're methods because of the different way in which they are called. They're called using dot syntax. And methods are a thing that we're going to talk about when we get into class. The way that you should think about it for now is that a method is like a function, but it applies to some specific type of object. So lists are a type of object. They are, technically speaking, objects that are instantiated from the list class. So these are methods which the list class has definitions for. By far the most useful one that you will ever use is append. Append just adds something to the end of a list. So L1.append. Yes. You can see that yes gets put at the end of the list. Extend works very much like the concatenation operator. So if we do L1.extend with L2, and then we want to see what L1 is, you can see that's basically just a concatenation operator. Don't ask me why they have both. Python is supposed to not be able to do stuff in two different ways, but that's the difference between designs and reality. If you wish to insert some element at some index, you first specify the index and then the element you wish to insert, and you use dot insert. Dot remove removes, it deletes the element at the indicated index. The dot pop not only deletes the thing that's at index I, but it also returns that element as the return value of the method. And if you wish to reverse the list, you've got dot reverse, although it is fewer characters to do that. That's the Python Pro quick reverse. You know, someone has taken someone's at least like looked into it or read a book or something if they use that. So, oh, I have a question. Could you please email me the slides as an attachment, please? I seem to be unable to log in at the moment through D2L. Oof. Would somebody else mind doing that? Sorry, Allie. It's just that, you know, I'm kind of teaching a lecture and I don't want to log into my email right here, right now, because, you know, security and privacy issues and all that. I don't want people seeing my email. If someone else in the stream wouldn't mind emailing the slides to this person. Okay, I have a question related to the subject. So for L.remove, if you put at 2, for example, it'll just delete the character at that specific value. Yes, let me demonstrate. So, doop-be-doop. So if we want, let's just get rid of some of this. L1 dot remove 2. Let's see what L1. Notice that the value at index, oh, interesting. That doesn't appear to be 0 indexed. Well, well, well. That's news to me. Well, that is, I am genuinely gobsmacked that that isn't 0 indexed. I don't know why that is. Why would they ever do that? That's so stupid. Why wouldn't you make it consistent? What happens if you do 0? Yeah, you get an error. What? What? That's so crazy. So what happens if you... So 5 is... Wait. Am I modifying this list after? Is this... I'm not adding anything to the list. No! So crazy. Okay, so pop is the same as remove, except you get a return value out of it. So there. See? What? Now it's working? Oh, sure. Pop is 0 indexed, but remove isn't. What a crock. That's so stupid. Anyway. So, my goodness. My goodness. Let me just catch up with chat a little bit. Oh, does it? Is that what it's doing? Am I stupid? Am I stupid? I might be stupid. Yeah, I'm stupid. Sorry, guys. It's actually searching for this element and deleting that element. It's not, this isn't the delete at index. Oh my goodness. To think that they put me in charge of people. No. Okay, then the slides are wrong. Because the slides say delete the element at index I, and that's I. No, it's delete the element E. This should be an E. The slides are wrong. I'm going to have them corrected. There. Oh boy. Anyway. So let's talk about aliasing. When I learned to program back in my day, I took a second-year course on C programming. And in C programming, you need to know about a concept called pointers to be able to do anything. The idea of a pointer is that your data structure has some address in memory, and that what you are manipulating when you're manipulating the variable is not, in fact, the memory itself, but the address to that memory. It's just interpreted differently via its data type. The idea of aliasing is that same concept in Python. And that's actually the way that things work in Python, which is demonstrated by the fact that you can do aliasing. So basically the idea is, if you try to assign if you have a list and you make a new variable that is assigned to that list, you're not copying the data structure. What you're doing is you're creating a second reference to the same area in memory. Yeah. So it's like this. This is the aliasing. This is the Octothorpe aliasing demonstration. There we go. So if we have two lists, L1 is 1, 2, 3, 4, 5, and we have L2, which is equal to L1. Obviously, if we print L1 and we print L2, we'll get the same thing. Question, what if the element 1 appears several times in the list? I can answer that quickly. Let's just insert 1, and it removes the first instance of the number that it's looking to remove, or the value that it's looking to remove. So, obviously L1 and L2 are the same. But how the same are they? If we, after we assign L2, if we make a modification to L1, say L2 is equal to 10, the question is this going to be reflected in L2? Oh, look, it is. While we are not actually making any direct modification to the variable called L2, this hypothetical container for duplicate data, what we're actually doing, L2 is only a reference to the original data structure. So when you ask L2 to print, what you're doing is you're saying, okay, I've got this address, I have to look at this data. This data has been modified with this operation, so it's both the same. Yes. So this is the concept of aliasing. And this can be tricky, right? Because it looks like it looks like it should be a completely separate thing, right? This looks like it should be a duplication of the data, but it's not a duplication. To your question, then, how would you remove an element at index L? Use pop. Pop does that. So, yes, aliasing. You can see in this example, if we append this list with 4 using concatenation, and we print them, we both get the same thing. And with this example, if we print them, then we get a different thing. there are certain operations which break the aliasing, right? So generally speaking, when you're thinking about list operations, there are mutating and non-mutating operations, all right? And like this is going to get kind of tricky. So a mutating operation transforms the data without breaking references. Mutating operations include all of the ones in this list. Notice like things like append, extend, insert, remove, pop, and reverse. All of these are mutating operators. So they mutate the code, they change the code, but they don't break any references. The references remain intact and in whatever sense they were before. However, a non-mutating operation does break references. So my favorite example of a non-mutating operation is concatenation. When you concatenate two strings, what you're doing is you're creating a new string that is composed of both of the old ones and deleting the old ones, essentially. Only if you're doing assignment, though. So it's the difference between being able to do one of these guys all on one line, right? And having to make an assignment back to the original list. So if you're making an assignment back to the original list, what you're doing is you're overwriting the existing reference, right? So when you're doing that, odds are pretty good that you're using a mutating operator. So, for example, if we go back to our mutability example, that might be better. If L1 is equal to, we'll need an L3. If L1 is equal to L1 plus L3, then what do you think is going to happen to L2? Well, L1 is L3 concatenated on the end of L1, right? It's 1, 2, 3, 4, 5, 6, 7, 8. L2, it has the old value of L1. So what we do is that after L1 has had this been assigned the value of this concatenation has its new memory. It is a new segment of memory that has a new memory address. When we take that memory address and we assign it to L1, we are overwriting the old memory address that was stored in L1. When we do that, L1 now points to different memory than L2 than it used to, but L2 is still pointing to that same memory. That's why L2 has not seen the changes reflected that were made when we made this concatenation operation. It's because the concatenation operation produces an entirely new memory address and writes that into L1. And of course, L3 is also not affected in any way, shape, or form by this operation. So, I don't know, hopefully that's making some sense. Is that making some sense, guys? I hope so. Mutation, aliasing is a bit of a tricky business. So the reason that it's important for all of you to know this stuff, right, is that if you are using the memory wrong, essentially, if you're not aware that this is what the computer is doing, there are some unintended side effects that can happen. This can be a source of errors inside of your program. Like, for example, we learned last class that when you create a function in Python, oh goodness, what are they called again? Actual parameters and formal parameters. The formal parameters, as used inside of the function, the values are passed from the actual parameters to the formal parameters by assignment. So what that means is that if one of the arguments of your function is a list, what's getting passed into the function is an alias for that list, not the list itself. This means, and this is super important, this means that if you make modifications to the list that has been passed by assignment into a function and is an alias, any changes that are made to the list inside of the function are reflected outside of the function. Any changes that are made inside the function will continue, they'll persist, they will continue on past the point of the function termination. Normally, this is not the case. This is not the case with a regular variable. In a regular variable, the modifications that are made to the formal parameter inside of the function, if you choose to do so, have no effect whatsoever on any variable names that are supplied as actual arguments. So, in the case of lists and other mutable data structures, this is not the case. And in fact, you can use that to your advantage, which, you know, sometimes it gets a little bit troublesome to be passing multiple things out of a function. You know, it's not a thing that a lot of programming languages support, and you might want to get used to not doing it or something like that. But what you can do is you can use this aliasing property to make adjustments to some underlying data structure without having to pass it back out of the function using a return statement or a compound return statement. Okay, I'll try it. So, Nick W. asks, could this cause a memory leak in a program? No. Python, what causes memory leaks, generally speaking, is bad garbage collection. So, I don't think so, not in Python. I will get to explaining it like you're 5. I'll try that. We'll see how it goes. So if you had an alias in a function, is that kind of like a global variable? Yes, it behaves in a very much a similar manner to a global variable. The alias itself, like the memory reference, is locally scoped, right? But it points to something that is of a higher level of scope. So yes, it acts like a global variable. And could you do an example of modification of lists and functions that continue outside of the function? Yes, I could do that fairly easily. So let's do something. Let's say we define a function, def do stuff, takes some list, Greg, for no particular reason. If we, I don't know, greg.append, it's Greg, and then we return true for no particular reason. There's a function. It's performing a mutating operation on Greg, the list Greg. And like that's the other thing about this, though, is if you use a non-mutating operation on it, you're breaking the reference, right? So you can do it, but you have to only use mutating operations. So if we then do stuff to list 3, for example, print list 3, see that it's Greg. Oh, Greg with 2 G's? Okay. There we go. So there you go. We have this list, L3. We pass it into the function doStuff. Notice that we are not even doing anything with the return value of this function. Ordinarily, that's required, right? That's required in order to get some information out of a function execution. I used Greg F, Greg G with 2 G's, not Greg of. There we go. So you can see that the modification that's made inside of the function is reflected in L3, despite the fact that it's never, pulled out of the function. It's the modification is made to the memory specifically. So I guess I will let your noggins nibble on that one a little bit. We will resume our lecture live stream at 6:30. Hello! We're back. So I thought about this a little bit. In response to explaining aliasing like you're like you guys are 5 years old, let's try this. So, you're in a playroom. Billy and Sammy both think that they built a castle out of blocks. Right? So if you go up to Billy and say, Billy, show me the castle you made out of blocks, he'll point to this specific castle made out of blocks. And if you talk to Sammy and say, hey Sammy, show me the castle you made out of blocks, Sammy will also point to this same castle that was made out of blocks. So, if either Billy or Sammy changes the castle, right, adds more blocks, puts a tower on it, whatever, both Billy and Sammy, when they are asked to, oh God, I'm not mic'd, right? Okay, good. If the castle has been modified, changed, if you ask Billy or Sammy to show you their castle again, both of you they will both show you the modified castle because it's the same castle. The point is to understand that they both think that they've made their own castle, but they've both only made one castle. That's the takeout. Maybe that's good. How did I do for explaining it like you're 5? Ah, okay. Matthew likes it. Okay. Anyway, we got a lot of slides to get through because I've been dilly-dallying, so yes. I've kind of explained all this. Okay. So, here's a question. What is the value of E at the end of this sequence of operations? We've got A is 1, 2, 3, B is A, C is 4, 5, B, A0 is C1, D is C2, and E is D0. Good. I'm glad. Yeah, if you guys, like, that's actually a really useful thing. If I get too wrapped up in what I'm talking about at any point, please ask me, can you explain that more simply? And I will do my best. So, cool. So, what do you think? A, B, C, or D, or E? 1, 2, 3, 4, or 5? This graphic on the side here will help you. Am I pointing at the slide? I think I'm pointing at the slides. Yeah. So a lot of people are, it seems, the preliminary results are in. Most people are split between either A1 or E5. So let's go through it. A is 1, 2, 3. B is an alias for A. C is 4, 5 plus B, which is an alias for this same initial array. If A0 is equal to C1, C1 is actually 5, so 5 gets put into a this thing that everything's pointing to, so it becomes 523. Then D is C2, C2 is this guy, so this is another reference to this same initial data structure. E is equal to D at 0, so the answer is E! The answer is E5. So, let's move on to a different topic. Let's talk about slicing. When you're slicing, what you're essentially doing is you're taking one of these linear data structures and you are saying, okay, give me all of your values from here to here, and I want you to step by this much. So, the best way, I think, to get the idea for that, get a feel for this, is to try it out with your handy-dandy Python interpreter. So, I need to... actually, that works. So, this is like indexing for awesome people. So, if we have some string, for example, this works on strings, lists, tuples, all things that are indexed numerically. So, what's it gonna take to get some service over here? That will be our string. If we want to take, and I think I've already demonstrated this a little bit, with slicing, there are 3 spots for numbers. You've got the first slot, the second slot, third slot. The first slot is the index that you start at. So, if you want to start at the 6th value, then that would be the apostrophe here. So, is that correct, though? 1, 2, 3, 4. Oh. I was mistaking. Yeah, okay. Never mind. It's right here. That's correct. Yeah. That's 6 characters. Sorry. So, anyway, if you leave these blank, they have default values. If you leave the second one blank, it assumes you want to go to the end of the string. If you leave this third one blank, it assumes you want to count by ones. So if you wanted to count by 3s in this case, there you go. That is every third letter starting with the 6th letter. You can see that's 1, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6? Yes. 1, something like that. Anyway. Or no, it should be counting by 3s. Pardon me. So this is every third character starting from the 6th. If you specify a value in the middle here, like, for example, 19, then you get a slice out of the middle of your whatever it is that you're slicing. This is cool. If you leave the first one out, it assumes you mean from the beginning of the list, which is the default. That's what the default value is. So there's some pretty cool stuff that you can do with slicing. There was at one point, on last semester, I wrote a test question that had a it was a card dealing algorithm. So the idea is that you had a list, or you had, I think it was either a list or a tuple. It doesn't matter. That was, this is just for a demonstration. But the idea is you had some list of values, and you wanted to essentially deal them out like cards and return a list of, I think it was a list of tuples that contained all of these elements, but you dealt the first one into the first one, the second one into the second one, etc., etc. And when you came back around, you started dealing them out again. There's a really easy way to do that, actually, using slicing. So the quick and dirty way of doing this algorithm, which ended up, you could actually do it as a one-liner, but only if you use slicing. So the solution went something like this. Actually, it was counting by 4. Yeah, make it a tuple. There you go. So, this stuff is really powerful. You can do a lot of, you can accomplish a lot of stuff relating to strings and lists and that sort of thing using slicing. So, yeah. Oh, and while I'm on the subject of things that might be useful for a test, hint, hint, wink, wink, nudge, nudge. If you have something like a string, what's the deal with this guy? If you want to break a sentence into words, there's a quick way of doing it. And that's using split. You can split on space, and that breaks a string. Basically, it breaks a sentence into basically breaks it into its individual words. The spaces, the thing it's splitting on, are not actually included in the final list of elements. So that's cool. Recommend learning that. That's a super useful thing. And I'm not sure what the inverse operation is called, but in Python I'm not sure what it's called, but in Haskell it's called intercalation. Anywho, back to slicing. So, oh my goodness. So normally this slide is a quick fire round. Like if this were an actual class, this would be a quick fire round with people raising their hands. But since it takes a good 30 seconds to get a response, I'm going to leave this slide as an exercise to the reader. Oh, however, there is one important thing that I should note before I move on from this topic. Please note that the second parameter here, this is, if you enter a number in here, it will end up being 1 minus the thing that you're actually trying to deal with. So, for example, if we just comment that out for a moment, something from the beginning of the list to element 10, for example, notice this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 characters. But this is the 9th index, right? It's 0 indexed, so the 9th element is the same thing that this guy stops at. Oh, come on. Don't do me like this. See? The 9th element is the last element here, right? This is 1 plus the stopping point. That's just a... Oh, join. There you go, join. You can probably specify a parameter there, which allows you to insert something in between as well. So, in theory, something like... Oh, yeah, that would be string. So join... This should do nothing. This should be what we call in the business an idempotent operation. Syntax error. End of line. Oh. What? Oh. That would do it. List attribute has no list object has no attribute. Join. Very interesting. So what does join even do then, if it's only applicable to strings? Weird. Anyway, I'm not going to... replace the with x or any other value. Well, it's space, right? It's supposed to be space. Well, anyway. Anyway, I'm going to leave this one as an exercise to the reader. So, just to cram that into your craniums. Oh, you put the string within the parentheses? Oh, okay. We'll try it one more time. Is it space dot join that? We'll see, won't we? Dot split. Ah! There you go. Thank you. Thank you, kind people. I just want to say, putting the separator in front makes, like, no sense whatsoever. I'm just gonna put it out there. This seems bass-ackwards to me. Anyway, in summary, tuples and lists are very similar. Lists are mutable, lists do aliasing, tuples do not. Tuples are faster, and lists are slower. Cool. So, let's talk about sets. So sets, the sets that we're going to be talking about here are sets in the sense of mathematical sets. So if you remember all the way back to high school, you may have done some rudimentary set theory type analysis. At least they used to when I was in high school. I get mixed messages about that these days. I think you only get it if you take like calculus in vectors or some gosh darned thing. I'm not sure exactly. Set theory is really cool though. Sets are the most fundamental mathematical system that we have yet developed, in that you can derive the entirety of the rest of mathematics from set theory. Like arithmetic is a derivation of set theory, and there are a number of also very cool other results that you can get from set theory. Frankel-Zermelo set theory is my preferred one. But anyway, the mathematicians in the crowd know what I'm talking about. So, a set is an unordered collection of objects. One of the classic mental examples of sets that you see is you have a bag, and you have a number of marbles, and the marbles are all different colors. And if you reach into the bag, you don't know which marble you're going to get, but you're going to get all of the marbles eventually. Okay, I have a question about the test. Let me just answer this one quickly. Will the test include the last 2 weeks' lecture plus next week's lectures, or just these 2 weeks? The testable material, generally speaking, I do not include the material that is covered in the week that the test is in for the test that is that week, because that just seems a little cruel to test you guys on an assignment that hasn't even been due, if that makes sense. So the testable material for this the test that's coming up next Saturday will be slide sets 1, 2, 3, and 4. So I think that's a reasonably robust answer to that question. So I'm not going to expect you to do any type conversion or binary representation stuff, or any functional stuff, or recursion-based stuff. Although I have released the assignments for that material, that's not going to be on the test. The reason that I released those assignments, I've just kind of been releasing them haphazardly and quickly. The reason for that is that this is a summer course. People's schedules are weird. People's schedules are weird generally lately. And if you have time to work ahead on the assignments in the course, I don't see any reason why you should be prevented from doing that. Excuse me, considering it's a pretty short course. Yes, to confirm, this is slide set 4. Topic number 4. Says so at the top. So, anyway, sets. So, numerical examples. The set of all even numbers less than 10 is 0, 2, 4, 6, 8. But the idea of these sets, it's going to be a fairly pivotal one, pardon me, is that there's no repetition. So, we have... Oh, I have other questions? Yes, you will have received your feedback from assignments 1 and 2 by the time you have to write the test. Ordinarily, the goal is to get those back on Tuesday, but the TA who handles that sort of thing had a bit of a medical thing, not COVID-related, thankfully, just kind of a general medical thing, which I won't disclose because, he didn't disclose it to me because it's personal. Anyway, he just needed an extra day, so today is the extra day. Anywho, so in set theory, we have a number of set operations, and you can think of these in terms of like the Venn diagram. Let's see. I think I can pull something up quickly. Set operations. Get me a Wikipedia article, please. Zap! Oh, that's a good one. So, oh, don't you hate it that you have to like right-click and view image to like see the actual image? It just takes you to the website if you click on it. Anyway, so you've got union. So union is, if you have two sets A and B that overlap, union is everything that's in A and everything that's in B. Intersection, you have everything that's in both A and B. In this sense, union can be thought of as similar to the Boolean OR operation, and intersection can be thought of as similar to the Boolean AND operation. And if you look at the actual symbols for these operations in formal mathematics, the intersection is like a upward facing curve like that, and Boolean conjunction or Boolean AND is a triangle in the same way. Union is like a U, which I guess kind of makes sense, and Boolean OR is a V. So they're, that should indicate how similar those operations are. Then we have difference. So given A and B, difference is all of the things in A that are not in B. And of course, cardinality, which is just the number of distinct elements in a set. This symmetric difference is not one that we are we're going to talk about. So let's set up sets. Ha ha! If you wish to declare an empty set, you declare set with empty braces. If you wish, I'm just going to whoop there. Rip. I'm going to escape. Can I escape? Can I? There we go. All right. Ha ha! Victory. So if we have S being a set, the way that we declare a set is with curly braces. Curly braces are just the most fun. Yes. So let's do it with just numbers. There you go. Interesting property of sets. If they are declared with repeating elements, those repeating elements will be removed because a set does not have repetition, which is interesting. So let's set up, actually, let's make it A and B. Just give it some random numbers. There we go. A or B. This is usually OR, by the way. This is union. So this is all of the elements that are in both A and B, while preserving the non-repetition of elements. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, because all numbers are represented here. Intersection is all of those elements that are in both A and B. So in this particular case, that is just 3 and 6. The difference between A and B is all of the elements that are in A but are not in B. So it is the original condensed version without repetition of A, missing the 3 and the 6 that are in B and are also in A. Cardinality is, of course, this now hopefully very familiar length operator that tells you how many things there are in the thing. And we have the test for membership. There you go. So, I have a question. Dictionaries and sets are using the same parentheses. Yes, sir. Dictionaries and sets are using the same parentheses. That is because basically dictionaries are sets, but without the restriction on repeated values, and you get to index them with whatever you want. Makes them kind of cool. So that's your basic set operations. So we also have operations that will modify the set. If you wish to add an element to a set, there is an add method. So a.add 12, print A. You can see 12 gets put in there. If you wish to remove something, there we go. You discard. There we go. And if you wish to remove an arbitrary element, you use pop. And of course, you can then assign that to something, and you can see what it is. There we go. So I don't necessarily want to get into it too much with this pop operation. However, this is like traditionally a sticky sort of thing to explain. Oh, I've got a question. Shouldn't cardinality be 4 if it's the number of unique elements in A? But my friend, the number of unique elements in A is 6. Okay. Oh, that I did that after the pop. Jeez, that'll do it. That'll do it every time. 1, 2, 3, 4, 5, 6. Length. Cardinality is 6. So the deal with pop, it's arbitrary but deterministic. This is a difficult thing to get conceptually. It's like, let's imagine that I'm going to try using I'm going to try to use the playground metaphor again. So let's say that you are playing on the playground and you get in trouble for no reason. What has actually happened is that you have run up against a set of rules that are arbitrary but deterministic. That the idea is the rules exist, but you don't know what they are, right? From your point of view, they are arbitrary. They could be made up. They can be made up for no particular reason. There's no rationale behind them. There's no method of operation. There's no method to them. What that often means in the case of a computer system is that the system is so complicated behind the veil that you can drive yourself mad trying to understand how the computer has determined that this is the way it's going to operate. However, because although you don't understand the origin of the rules or the rules, the fact of the existence of the rules is that can't be argued. And because there are rules, it will do the same thing consistently, although the thing that it does consistently won't make any sense. So in this particular case, I'm pretty sure I can get this thing to change the way that it looks if I move some of the values around. I might not be able. This might not actually work. No, it's not working. Just because this set is displaying these numbers in numerical order does not mean that values are stored inside of a set in numerical order. It is correct to think of the values inside of a set as being stored in no particular order. A set does not imply an order. It just implies a collection, right? If you think about lists and tuples and strings, these are ordered collections. These have a linearity to them, right? You can tell where you are in the set by a particular number. That means that it's ordered. In a set, in the purest sense, the type that we're working with here, there's no ordering to the elements inside of it. Because there's no ordering, which particular value is going to be popped out of it, this is going to change depending on the set, and it's not going to be obvious how it changes. Yeah, Nick W says, dang, maximal speed of light not letting me go faster than 300,000 kilometers per second. Yes, but if space is being stretched around you in such a manner that your speed relative to your local your local spatial distortion is underneath that threshold, you can achieve speeds faster than your local speed of light restriction within the context of the larger universe. That is how the warp bubble from Star Trek works, and there's a theory that you could actually get that to work in reality. However, it would take most of the energy in the universe probably to make it work. Could you change it into a tuple to tell the original order? Well, that's an interesting idea. Let's run a little bit of an experiment. What happens if we tupleize it? Yeah, so it's displaying it in the order that it's displaying it. Not a physicist, just a nerd. A nerd with a mission to educate people. Yes, that's... I'm not sure I could trust myself to pronounce it, but Mars Lettuce has told us the name of that drive, the warp drive, the warp field. The warp... Yeah, yeah, warp field drive. Anyway. Personally, I think wormholes are probably more probable as a means of FTL. Like, again, it would probably take a substantial amount of energy to open up a wormhole, but once opened, if you could stabilize them, you get point-to-point transfer without having to worry about time, which would be like the ideal case for like in theory, even if you had a warp drive, you're still like it still would take a long time to travel astronomical distances. But yeah, anyway, it gets interesting and complicated. Anyway, so what were we talking about? Oh, yeah, okay. So with respect to sets, there's like a couple of neat things that you can do with sets, but they are largely used for academic purposes. Like, they're not extremely practical from a computing sense. They're kind of a thing that's reasonably unique to Python as well. However, they're of interest for people who have more of a mathematical background. If you're doing really mathy stuff, you might need sets. Just move space instead of moving yourself. Yes, if I had a sufficiently strong fulcrum and lever and enough of a size, I could move literally anything in the universe. Anyway, so it's possible to get me all of the unique elements in a data in a collection by changing it into a set and then possibly changing it out again. This is a lot of jiggery pokery, and I'm going to show you how to do it in one line. So if you have, let's say you had a, actually, we maybe use one of the ones from here? Nah. So if we have a tuple, it's got to have, actually, this will do. Yoink. So if we have a tuple that has repeating elements in it, if we want to isolate the minimal set of elements in there, all that we really have to do is print the set interpretation of that tuple. There you go. And if you want, you can always convert it back to a tuple. And then you get all of the unique elements in that set. And I realize I'm going through this a little bit quickly, but we actually have quite a lot of ground to cover and not a lot of time to do it in. So that works. Again, this particular slide is intended as another one of these quick fire rounds. with respect to, what's the output going to be. And normally we would raise hands, but because that, it takes like 30 seconds to do each one of these, I think I will leave this once again as an exercise to the reader. So here we come to another summary. Here we go. Lists, tuples, and sets. Tuples use round braces. Lists use square braces. Why didn't I use that before? Okay. And sets use curly braces. All right. In tuples and lists, you allow duplicates. In sets, there are no duplicates allowed. In tuples and lists, order matters. In a set, the order doesn't matter. In fact, it doesn't exist. Tuples and lists, tuples are immutable, also strings. Lists are mutable, and sets also mutable. So if you remember all of that aliasing stuff that we talked about during the first block, that all applies to sets as well. Questions? Would .index not work on sets? Good question. Let's see. .index of 8. Yep, attribute error. Index set object has no attribute index. Index is not defined for sets. So let's get to a cool one then. Dictionaries. So dictionaries are a bit of an adjustment. Think lists, but you can index them with literally anything. So it's actually a more general structure than a list, because a dictionary could be a list if you made all of the indexes a sequence of numbers. However, in dictionaries, you can do so much more than that. So, for example, if you wanted to write a dictionary that told you the number of days in the month for any particular, for the first 4 months of the year, you get a value out of that dictionary by indexing it with the string rather than with a number. So I'll just demonstrate this for you real quick. Days in month February, 28. So another way of thinking about one second for your question. Another way to think about dictionaries is as a mapping between two types of data. So if you have a value that maps to another value, even in a different data type, then a dictionary might be appropriate, as if you can't express it with a function. So I have a question from Tef. Why does order matter for a tuple? Well, because the order is preserved. When you declare a tuple, basically what it means when it says order matters is that things can be accessed sequentially, right? So if the order didn't matter, you wouldn't be able to access things sequentially, right? You wouldn't be able to say element number 7 is this, element number 32 is that, because the elements 7 and 32, that wouldn't make any sense, because this is just a blob of data with no way of knowing what came first or second. Hopefully that answers your question. So this is some pretty important nomenclature right here. When you are talking about dictionaries, you have keys and values. The key is the thing that you're indexing by. In the case of days in month dictionary, that is January, February, March, and April. Those are the keys. The values are the things that are pointed to. So 30, 31, 28, 31, 30. these are the values. And you can have functions that can extract from a dictionary just the keys or just the values as well. And we'll get to that in a bit. I have a question from a person who is confused. Literally, how do you differentiate between a dictionary and a set just by looking at it? Answer, a dictionary has colons. So these colons are put in between the keys and the values. So this is an entry, January 31st, or Jan colon 31. That is an entry in a dictionary. It is composed of one key and one value. And that's the difference between this a dictionary and a set. In a set, you don't have the colon. It's just one thing here. This is a mapping, though. Yes, I'm pretty sure sets can have like strings and stuff too, though. Let me check this for a moment. Yeah, sets can totally have. Ah, okay. So this is a good example actually, because this. Sorry, just to go back to sets for one teensy little moment. This is a good example of this property that I was talking about with respect to sets. The order is not necessarily meaningful. So if you take a look at this here, well, now that I look at it, it looks like it's just put it in ASCII order because the W should be in ASCII before this rest of it. So when it's printing it, it's automatically sorting the elements according to the ASCII values of the characters that are in the string, but you shouldn't rely on that, and you should not think of a set as a thing that contains ordered data or sorted data. Is this why the structure of registry editors looks familiar to this and uses the same terms? Yeah, so you'll find that I'm actually not familiar with registry editors, Mr. Nick W, but this is also a thing that exists in JSON files. This sort of structure, it's reasonably a lot of things have adopted it. So yeah, hopefully that answers the question. So with respect to dictionaries, we have once again one of our quick reference cheat sheets for dictionary operations. If you wish to declare an empty dictionary, and for those of you who have been thinking, oh my goodness, why would you ever need to declare an empty one of any of these? The answer is so that you can write a loop that populates it, right? If you start off with an empty data structure, and then you have a loop that generates all the values in that data structure, and then outputs the data structure at the end, based on some criteria, that is a test question, my friend. So you should learn what an empty dictionary is, and an empty list is, and learn how to add stuff to it inside of a loop. There you go. Specifically, Windows systems have a registry that essentially acts like a dictionary for everything installed on a particular PC. Yes, I think the Windows registry probably predates Python, but, you never know. So, again, if you wish to create a dictionary, the notation for that is curly braces, entries, where an entry is a key and a value separated by a colon. If you wish to look up a particular key in a dictionary, you do you use square braces, as we demonstrated. If you wish to look up to see if a particular key is in the dictionary, you use E in D. So notice this is kind of important. This is a specific default behavior. So this test for membership that we've been doing, Feb in days in month. In the case of dictionaries, this is you're assumed to want to know if February is in the keys of the dictionary, and it turns out this is actually kind of intelligent. However, if you want to see if February is in the values of the dictionary, then you have to do .values, as will be demonstrated on the slide. So if you want to get a tuple containing all of the values that are in the dictionary, you use d.values. If you need to use it, if you want a test for membership of the values of a dictionary, then you have to use d.values in where d is here. If you wish to delete a key, E, and return its value from D, you use del. So delete from dictionary. Again, len tells you the size, and if you want to get a tuple with all the keys, that's d.keys. It might be slightly informative to show you guys what that looks like. So days in month.values, print that, also print the keys. There you go. Notice these aren't just straight tuple objects. These are, in fact, inside of wrapper objects, but you'll probably be able to index them with no trouble. Or not! Okay, never mind. Oops. No, wait, I did that wrong. No, okay, so that's not a subscriptable thing. So you would have to then also convert to a tuple. Would this work? Invalid syntax. Oh, yes, I suppose it would be, wouldn't it? Tuple. Tupleize me, Captain. There you go. That works. See, the thing about programming and Python is that if you're trying to do something and it just isn't quite working out, you can probably find a solution to your problem by fiddling around with the syntax a little bit. But, it depends on what you want to do. It's very contextually dependent. Anyway, that is this slide, and I think we will break there for the break. Thank you very much, everybody. We'll see you back here at 7:30. Hi, folks. So, my other cat he doesn't seem like it right now, but he was kind of miffed that the little kitten got all the attention on the stream and he didn't get any. So this is Martin. He's a big boy. Say hello to the internet, Martin. He's like, I don't want to be here right now. Wow. So this is Martin. He's huge. Look at this. Look at this guy. He's enormous. He's a Maine Coon Bengal mix. He still gives kisses, though. Hello. Be free. Anyway. So, with respect to your question, right? With respect to your question about the assignment, if you could shoot me an email about that, I would be happy to answer it. Oh, come on! He also likes knocking over glasses. Jesus Christ. Thank you. And the scream was going so well, too. Thank you. Anyway, cat, bringer of chaos. Yeah, unfortunately the cat also yeeted my water glass, so... Yeah, he got his revenge. Yeah, he is a chunky dude. He's actually a year old, and he's not actually a fat cat, because he's part Maine Coon, and if you've ever seen a picture of a Maine Coon cat, they're quite fluffy, right? So he's actually like mostly fluff under there, but you know, he's also just physically large, right? Like, yeah, you're right. He is around 15 pounds. So, yep. Anyway. He's a year old. A year and a bit old. Anyway, so let's move on. Let's do some more examples with dictionaries. So, cat hair in my mouth. So, burp, nope. Hip, come, okay. We have an enrollment dictionary for hypothetical enrollment sizes. If we wish to update this to reflect the enrollment numbers that we had last semester, it was something more like that. The enrollment for this class has been going up quite precipitously over the years, actually. Some of you may have noticed that like double the number of slots were available for this offering as opposed to the previous year's offering. And, you know, that was kind of just like market forces. If there's a lot of demand for something, then there needs to be an increase in the supply. So, anyway, dictionaries, and I'm going to spell it with 2 L's, just because I roll that way. These are also mutable data structures. So, something like an assignment operation is totally valid. Additionally, if you wish to add an entry to a dictionary, it's actually quite simple. You just use assignment. If you assign to a dictionary value that has not been used yet, then it just adds it to the dictionary. This is a super, super handy thing to know. Sorry, pardon me. Can I zoom in? That is hopefully a little better. Sometimes if the lines are too long, it gets to be problematic, but yeah. Anyway. Well, it's interesting actually to your comment that COMPSCI is where all the jobs are. That used to be very true. That was definitely true in like the .com boom era of like the early 2000s or the early noughties. But as time has gone on, software development has ceased to be the boom town that it used to be. It's kind of stabilized as a profession, and like the number of people who are like the number of software developers that are employed has been relatively stable for the last 5 or 10 years or so. Maybe not 10 years, but 5 years at least. So like if you were expecting it, like if software was still a booming industry, you would expect the number of people employed as software engineers or software developers to be increasing every year, but it's not really. It's a stabilized profession, so that not that there aren't jobs in it. There certainly are jobs in it. It's just don't go in expecting everything. Don't expect a guaranteed position just because you know how to program Python, basically. So, yeah, anyway. Slight tangent. Yeah, so anyway, dictionaries are mutable. That's the point. Here's an example. We can use a dictionary to construct a histogram. So if you remember back from, elementary school, histograms were among the first charts that you would have been taught to do. Histogram, what it does is it counts the frequency of something that occurs inside of a collection. So let's say, rather than just deleting all the excess entries, in this case, we are going to histogram some, let's say it's a list. First, we create a dictionary. This is a coding example. So D for dictionary is an empty dictionary. For element in L, can you guys hear that car alarm going off? Because I can hear that car alarm going off, and I'm wearing headphones, jeez. Oh good, it stopped. And it wasn't my car, even better. So, before we add a element to the dictionary, we need to see if it's already in the dictionary, right? Because what we want to do is we want to have one dictionary entry for every unique element in L, and then we want to populate, we basically every time we we want to go through L, and every time we look at an entry, we need to see, is this already in the dictionary? If so, increase its key value by 1. And if it's not in the dictionary, add it to it. So, if element is in D, remember that searches the keys, then D at E plus equals 1. Otherwise, D at E equals 1. It's a initialization problem again. If you used this line, if you used this line without having it set up the values, without having added things to the dictionary originally, I'll show you an example in a bit. then you would get a error here because D at E doesn't exist yet, right? So what are you plus one-ing? There's a broken reference in there. So if we want to try to use our histogram on a phrase, like the most recent comment, can you guys like not I'm trying to learn, which I think is a great comment, and then print it, return the result, because your professor is definitely not a big dummy. I'm definitely a smart guy. You can see what it's done is it's taken all of the individual letters inside of this string, and it has told us how many times each one occurs. So, for example, N occurs 4 times, space occurs 7, capital I appears once, etc., etc. So what would happen if we didn't initialize these guys? If we just said that, we would get a key error. Because we are trying to reference a key that's not in the dictionary, we say, key error C. C does not exist in there. What are you trying to do to me, man? Which is kind of related to the variable not yet used error that you sometimes get if you forget to initialize your accumulator. Matplotlib. Ha! You're getting ahead of me, man. Honestly, though, Matplotlib is a thing that we'll be doing in Chapter 11. I'll see if I remember it. Import pyplot. Oh my goodness. If X is the histogram, then is it? Oh my goodness. Oh my goodness. Okay. Let's take a look, shall we? So, Matplotlib is a Python library for generating actual graphs. It makes sense to actually generate a histogram if we are looking at histograms. Come on, load. Maybe download? Upload? Reload? Unload? Loady load? Boop, 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 boop. Boop, 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 boop. Boop, 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 boop. Well, anyway, we'll come back to that when it loads. So, another interesting point is that you can actually iterate over the entries in a dictionary using a for loop. So in the same way that they assume that you're trying to search the keys if you use in, they will assume that you want the keys here in the dictionary. What am I trying to say? It will automatically map the keys of the dictionary into K, rather than, in the case of a list, the elements of that list. So, and that's demonstrated quite clearly here. For K in enrollment, print K, you get C1, C2, and C3. For K in enrollment, print enrollment at K, you get 46, 150, and 0. So, good. Has this thing loaded? Not really. Why? Okay, we've got something. I think histograms are towards the bottom. My God. The internet is terrible. Is it just me, or is the internet terrible? Anyway, this is a sneak preview of stuff that we're going to be covering, like... Hist, pyplot.hist. Okay, there we go. If I use the slides for quick reference, you guys can use the slides. Pyplot.hist x. We'll see if that works. Pyplot.show. Do I still have an error? Did I leave an error in there? Oh. Matplotlib. No? Well then, show me what I'm doing wrong. Oh. Matplotlib, not mat. Okay. Matplotlib.pyplot. Perp. So, looks like it doesn't take a dictionary from a histogram. It just takes name error. But it is. Oh my goodness. All right. Really? As pyplot. Okay. Okay, so it just doesn't like dictionaries as well, which I thought it might not like dictionaries. So rather than histogram that, let's tuple it. There you go. That's a histogram. I know it took a while, but there you go. Thank you, Thomas Hankins. So anyway, that's how you can make a histogram without using dictionaries, which is kind of beside the point of me trying to teach you dictionaries. But anyway, so this slide is another one of those quick-fire rounds that we've had a few times now in this particular set of lecture slides, since, again, it takes about 30 seconds for me to get the responses from the class on any one of these particular ones. I'm going to leave figuring this out to the as an exercise to the reader. So, let's talk about some problems. Computing change. We shall talk about the change problem. Compute the smallest number of coins or bills that sums to the target amount. That is our problem. For example, in Canada, we have coins 5 cent, 10 cent, 25 cent, 100 cent, and 200 cent. If we have a target amount of 185 cents, then we can express that using 1 dime, 3 quarters, and 1 loonie. Sure. However, we want to find the smallest number of coins or bills that sums to the target amount. So, let's try to solve this as if it were an assignment problem. First of all, we need to identify what our inputs are. Our inputs are going to be a tuple containing a number of coin denominations as integers, and a target value as an integer. Yes. If I may make a recommendation to the people in the chat right now, perhaps that is the type of conversation that you want to have less publicly. Could we keep it, you know, about computer science, please, and related topics, and pop culture references are okay too, insofar as that's possible, please. Think about computers. Don't think about not computers. Anyway, so with respect to this problem, we've got a tuple of coin denominations, we've got a target value. The output that we're trying to achieve is a dictionary where the keys are coin denominations and the values are integers corresponding to the number of coins in the denomination that make up our answer. So let's attempt to construct said algorithm. Def coins. We shall take a tuple of coins and a target value. Let's use capital C and lowercase t for this. So we need to create a dictionary. At any rate, it doesn't really matter what your intention was with those particular chat messages. All that mattered was A, the impression that you were giving to the rest of the people who are trying to attend the lecture, and B, the fact that you have been interrupting the lecture with this type of talk. But anyway, let's get back to this. Yeah, could we maybe cut the drama? Would that be okay if we cut the drama and got back to science? So our output is going to be a dictionary. The dictionary is going to have all of the denominations of coins in it as keys. Since we have these key denominations up front, what we can do very quickly is we can establish what our dictionary is, populate our dictionary prior to trying to figure out how many coins of whatever denomination. I'm ignoring chat right now. Whatever denomination that we want to have. So we'll define our output as an empty dictionary. For coin in coins, out at coin is equal to 0, because before we figure out whatever we want before we figure out the answer to the question, what is the set of coins that we want for this target value, it's all going to be 0, right? That's a good default value in a lot of cases. So yes. So we have our target value, right? So there are a number of ways of approaching this problem, but let's go with a reasonably easy to implement, if a bit naive, approach first. So that approach, if you have a target amount and the denominations, a simple way of going through this would be to take the largest denomination, see if it's less than the current amount, and if it is, subtract that from that amount, however many times it would go into it, and then say that's the number for that amount, right? So let's do that. And I think let's assume that our denominations are in descending order. Assumes denominations are in descending order. So, for coin in the dictionary now, and let's say running value, let's just call it T2. Or let's just use T, that's fine, pass by assignment, whatever. If C is less than T, T minus equals, well, actually, T equals T mod, modulus C. So obviously the remainder of the division between the denomination and the target value will result in all that amount of the target value that can't be represented by whole parts of the coin denomination. So this is a perfect application for modulus. With our out at C, then that would be equal to, we probably want to do that first, actually. T integer divide by the coin denomination, and then T is equal to T mod C. This might even work without this if statement, now that I'm looking at it. But we'll keep it in there. And then we want to return our output. Okay, so let's test it. Coins. 200, 100, 25, 10, and 5, which are Canadian denominations. And let's say we wanted to do $4.79. Let's throw the penny in there too. Why not? $4.79. Syntax error. Uh-oh, did I forget a colon? I forgot a colon. Errors, errors, errors. Name D is not defined. What am I using D? I'm in out. Good lord. Okay, there we go. So, oh, there. So the error that I made was that over here everything is in cents, but over there I did it in dollars. So, okay, so there we go. 479 cents is 2 toonies, 3 quarters, and 4 pennies. So there you go. I know, I miss pennies. Pennies were cool. Find a penny, pick it up, and all the day you'll have good luck. So there we go. This is an algorithm that works. So let's see how we did in comparison to these guys in the slides. So, for one thing, there's a big difference right off the bat in that we have initialized our dictionary beforehand. So result is a dictionary. I is length of coins minus 1. So we're also, using a while loop here instead of for loops. But you can see that the core stuff, i.e. the integer division and, oh, they're not even using modulus. Oh, that's, yep. All right. If you want, you guys can vote in chat and say which one of these two solutions you prefer. Personally, I prefer mine, but you know. This is probably a very old example that dates back to the existence of, prior to the existence of for loops or something like that. Could you also add in a rounding function to deal with the remainder if you drop pennies? Yeah, you could totally do that if you want. The other thing that you could do is you could have it like output what the remainder would be as a separate as a compound return statement. But yeah. And these are the new slides too. I should have these updated with this too, but you know. But yeah, so that's an algorithm. However, it's important to note this particular type of algorithm, this particular type of approach that we took to this problem, this is called a greedy algorithm. So the general approach is, and this is going to be some like heady stuff, but in algorithmic design, we sometimes classify problems. We take a problem and we say, this problem, that's very similar to all of these other types of problems. This type of analysis is where the concept of NP completeness comes from, for those of you who know what that is. So and we'll get there in the next 20 minutes or so. So if you have a problem and you make a decision about it, and then that transforms the problem, into the same problem but with less things in it, this is what's known as a matroid, right? M-A-T-R-O-I-D, matroid, not metroid, matroid. Could I post the solution to the question on Piazza or something? I think that I will just take this notebook that I'm working on and post that, because that's got everything in it, right? That would be useful, I think. So, matroids are in the like with this particular question, if you take the target amount and you take one coin, you select one coin from the list, calculate how much that coin should be, you then can effectively remove it from the list, in your mind at least, even if you're not doing that in code, and you're left with the same problem, but with a reduced coin list and possibly a smaller total value that you're trying to work with. This is a typical formulation for a matroid. Now, the approach to a matroid type problem, where you take, basically at every step, you just take as much as you can, this is known as the greedy algorithm. So, in this particular instance, we calculate how many of the biggest coin will fit into the total value, and then we go with that, and we don't consider that coin anymore. Then we do the same thing with the next biggest coin, the next biggest coin, and the next biggest coin. This is a greedy algorithm. Oh, question. No, that's more unrelated stuff. So, with respect to this algorithm that we just wrote, the question is, like the original question asked us to compute the smallest number of coins and bills that sums to the target amount. Now, we've generated an algorithm that comes up with an answer to the question of how many coins can sum up to the target amount. It's by no means the only answer to the question. You can imagine you can just dump everything in pennies. That wouldn't be what we're looking for, though. We are trying to compute the smallest number of coins. So the question is there a scenario under which the greedy algorithm gives us the wrong answer? And the answer to that question is yes, in fact, it does. So let's consider some differently valued coins. Let's say that the target value that we're heading for is 14, and that we have a coin set that is 1, 5, 7, and 10, right? So in the case of our algorithm, what we'd end up with is it would look for the 10s, it would find 110, right? It would say, okay, 110, no 7s because we have 4 left, no 5s because we have 4 left, and 4 1s because we have 4 1s left. The optimal answer to this question, however, would be to say 2 7s. That's the smallest number of coins. And 2 coins versus 5 coins is actually off by quite a lot. So in this particular instance, guys, don't feed the trolls, eh? In this particular instance, the greedy algorithm only will give the optimal result if you make certain assumptions about the divisibility of the coins that are in the coin list. So if each coin is at least twice what the previous coin was, then you don't have this problem. And as you can see, that property isn't maintained for the set 1, 5, 7, and 10. So this is actually a hard problem. This is a problem that it's difficult. This is a Okay, give me one moment. I'll get into NP completeness as soon as I. It's too late to change things to Zoom at this point, and I don't think that. Well, the way that we can handle this, if we start ending up with trolls in the chat, which I'm not convinced that this is actually a situation that we're in currently, is if you at me with your questions, then I can pull them out a bit more easily. No, the stream isn't frozen. I was just reading the chat logs. So, yes. So, so to go over that bit again, where greedy algorithms don't necessarily produce the optimal result, the problem is essentially one of look ahead, right? So we have this idea of looking ahead into the future, as it were. With respect to the coins algorithm, looking into the future means looking forward to the coins that you aren't currently on, right? So, in this particular case, in order to get the optimal result, when you were on 10, you would have to look forward and say, oh, I've got a 7 coming up. And if I just hold off on assigning a 10, I'll be able to come up with a more optimal solution by choosing 7s instead of 10, 2 7s instead of 10. In order to do that, though, your algorithm has to be a lot more complicated. Like, things get super, super complicated really quickly when you start introducing these types of things, and you start running into like bogging down the runtime considerably. Like the greedy algorithm may not produce an optimal solution in a lot of cases, but it's used because it often generates a good enough solution in a lot of cases. So this is what's known as NP completeness or NP hard problems. So it comes down to the amount of time that you can run the algorithm in. So NP, the formal mathematical definition of NP completeness is a problem for which, or a problem that is a member of a set of problems for which there is no proof of the existence of an algorithm that can run in polynomial time. So, yes. The comment, so it chooses the local optima instead of the path that will lead to the global optima. Correct. That's a calculus-y way of thinking about it, but that's a good way of thinking about it. So yes, you can think of it. This is a somewhat underspecified problem, right? You can think of a vast number of different ways that you could come up to the solution, right? If we go back to the larger example, or even 185 and 510, 25, 10, 100, and 200. There are a large number of configurations of change that would be valid configurations of change. However, only a few of those are, close to the optimal result, and only one, possibly, is the optimal result. So, is this the last slide? That is the last slide. Okay. So I'm just going to be pontificating about NP hardness for the rest of the class. So, and it's kind of difficult to explain. The road I'm going down takes us through big O notation and runtime. So I'll give you the Coles Notes version. When we write an algorithm, what we're interested in when we talk about the efficiency of the algorithm is how quickly that algorithm's runtime goes up as we add data to the input. So the more you can think of it as, if a list is the input, the longer the list is, the more time it takes to operate the algorithm over that list. Math.floor, math.floor and modulus can be used interchangeably in some scenarios. So if the runtime of an algorithm, when the runtime of an algorithm increases, it doesn't necessarily do so in direct proportion to the size that's increasing, right? So if it does increase in direct proportion, i.e. it's a linear relationship, then we are in linear time. It is a linear time algorithm. This is like almost a best case scenario. The real best case scenario is logarithmic time. So the runtime increases according to the logarithm of the, it sort of does that, the logarithm of the number of inputs. In slightly worse territory, but still okay territory, we have the polynomial time algorithms. So you have, it might be proportional to the square, it might be proportional to the cube, but the idea is that as the input increases, the runtime will increase according to a polynomial function. So these would be P problems, polynomial problems. Linear problems, logarithmic problems, polynomial problems. Then we get into the bad algorithms. So rather than being proportional to n squared, And I realize some of I'm sorry, some of you may have to like watch this back a couple of times to get what I'm saying, but in rather than being proportional to n squared or n cubed, you can have runtimes that increase by a factor of 2 to the n, right? I.e., for every additional input that you add to the algorithm, the runtime doubles, or, does something similarly ludicrous. And you'd be surprised how many algorithms that this actually is the case for. It's a surprising number of them. But algorithms for which there's no proof that it is possible to generate a polynomial time solution to them, these are NP hard problems. And normally they're the types of problems that require look ahead. So think for an instance about, a chess engine, right? Back in, I think, the 80s or 90s, one of those things, computer scientists created a chess engine that could beat the top human players, right? And this was like generally considered to be the great overthrowing of human intelligence in the face of the master machine race. But, it ended up not occurring quite as quickly as they thought it would from that point. We're still here after all, but if you're going to build an AI that plays chess is such a sufficiently complicated game that you can imagine the analogy being, if you wrote a chess AI that always captured an opponent's piece, if it was possible to do so, that's not necessarily going to be the algorithm that wins, right? Sort of aside from the fact that a human player can detect a strategy like that and produce a counter strategy, and if the AI cannot counter a counter strategy, then it's not going to win, right? But, actually, if you're playing chess, just simply reducing your opponent's pieces as much as possible while taking the least amount of damage yourself is, like, it's right up there in, like, the meta goals of any particular chess game. Yes, I'm talking about Deep Blue and Garry Kasparov. That is precisely what I'm talking about. So the problem is that if you take a look at a chess game, that is a combinatorially complex game. If you look at the number of possible chess games that exist, like number of combinations of moves, I think it's something like there are over 1 million combinations of chess moves that could be made in the first 10 moves or something like that. So you can imagine, a chess game occurring, and like the thing about a chess game is that it's also inherently exponential, right? For each additional move, that explodes the number of possible chess games by the number of you multiply it by the number of possible moves. That's how combinatorics works. So the number of possible chess games that you have to consider is blowing up, right? You, as the programmer, have to devise some strategy for eliminating large numbers of them that might be irrelevant, making decisions based on, possible optimizations. But the problem with the optimizations is that you can only look so deep, right, before you get overwhelmed by the number of possible states. So this is essentially this is known as the state explosion problem, and it is a fundamental, it's a fundamental problem of computer science. Lots of things are vulnerable to the state explosion problem. The state explosion problem, incidentally, is also the reason that cryptography works. because cryptography operates on the basis that, if you have a random string of characters, the number of possible specific strings that string of characters could be is so stupidly high that it would be practically impossible for anybody to break it via brute force, i.e. trying each one. So I have a question about chess engines. Why is it that when chess engines play against each other, they don't just play the same moves over and over again? Because they don't have complete look ahead. These chess engines that you're referring to are probably spoofing a certain amount of look ahead by just doing a certain amount of randomness. I don't know what AlphaGo is. Oh, Go? Go is harder than chess. As a problem, Go is harder than chess, and as I'm aware of it, I don't know, maybe I'm not sure about Go, if computers beat humans yet. My understanding was that if they do, it was up to until very recently that the best computers could not beat master Go players. But yeah, Go is, combinatorially speaking, a harder game than chess. So it takes more computational power and algorithmic jiggery-pokery to get a Go algorithm to get up to the level of a human player than for chess, because chess is a numerically simpler game, right? It's like how they made checkers, master checkers AIs before they made master chess AIs. But anyway, the state explosion problem. This is a really, really fundamental limit. It's both a limitation and a restriction on computation. It's the reason passwords work, right? Because if you had, and quantum computing might blow everything out of the water, but in order to break a password, you would have to try every password, right? Unless you had some foreknowledge. If you can try, all of the combinations at once, which might be possible using quantum computing, then, all cryptography in the world is shattered before you, and you, yeah, if you, yeah. So we haven't been beaten yet. What was I saying? State explosion problem. Yes. So it's interesting because my classical example of this is that, or at least it's classical with respect to me as a lecturer. If you take a tweet, right, the characters that comprise a tweet, right, 140 characters. And I'm just going to do some Google math, right? So let's say you have 140 characters. Let's say that each one of those characters is encoded in 8 bytes. This is quite the assumption because they're probably Unicode characters, but let's assume for the purposes of this calculation that they're all 8-bit. Did I say byte? I meant bit. 8-bit characters, right? So that means that you have a total of 1,120 bits of data that are the memory that hold that tweet. So the number of possible permutations of that memory, the number of possible states, the number of possible tweets is actually 2 to the exponent of that number. 2 to the exponent 1,120. This is, I want you to calculate it. All right, fine. I'll use your calculator thing and not type it in. Jeez. Okay. So, yep. 2 exponent 1120. Ha! It tells me it's infinity, but it's actually not infinity. I think if you do half a tweet, it actually comes out to a value that exists inside of floating point representation. That's how big the number is. It cannot be represented inside of floating point representation. Oh, come on. Anyway, it's stupidly big. All right, how about a quarter of a tweet then? (2e to 80). Yes, I know. Anyway, if you take this number, right, let's assume that you can process 1 billion cases per second. And that's quite the assumption. But let's assume that you can process 1 billion cases per second. Right? Now let's assume that there are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days in a year. Oh, come on. This one. Divide by 60. Divide by 60. Divide by... Oh, I did it again. Jeez. Divide by 60. Divide by 24. I was getting my rant on too. 365. So this is like the number of years that you would need in order to fully calculate that number, right? It's like if you had 1 second for every atom in the universe, and inside of every atom there was another universe, and you had 1 second for every atom in that, or 1 year even for every atom in that universe, you would still not have enough time to calculate all of the possible combinations in one tweet. Yes, I think I've screwed up the calculator somehow. I'm just gonna close it. But just take my word for it that it's a stupidly large number. So, and that's NP hard problems. Ooh. You guys all have a tutorial to get to, and I have been delaying you. Thank you very much for your time and attention today. Next time I'll remember to turn on the big light in this room so we don't get my face looking like a, really bright thing. Anyway, I'll get that calculation at some point. But yeah, anyway. Cool. Thank you for listening, folks.